the polar coordinates and how to represent complex numbers and actually things in the rectangular coordinate system in polar coordinates. So last time we introduced the spider web. This was the polar coordinate system, and we could plot points in terms of their distance away from that middle point. We call that a pole, and their revolution from the positive polar axis, we called it. So I believe last time we talked about introducing how to transform between rectangular coordinate systems or regular Cartesian coordinates and polar coordinates and vice versa. And the good news is that it's exactly like the Pythagorean theorem. So you can see those definitions there. If you are given an XY coordinate in Cartesian coordinates, you can change it into polar coordinates. You can find that distance from the pole and that angle from the polar axis by using those conversions there. Good morning, Tomas. And it's just as easy to convert back to rectangular if you have polar. We've been using these a lot for vectors, things in the past. So our conversions there would be r cosine theta and r sine theta are equal to the x and y coordinates. So I wanted to go ahead and graph these. I think we were there last time. I think that's where we sort of ended up. I want to graph these following points in the polar coordinate system, and then we can label polar coordinates aren't unique. So we can actually label, we can find other points that are equivalent to this. So I want to try the first one, and then I want to give you all an opportunity. So if I'm looking at this first one here, just to sort of recap our understanding of these things. This one is 4, 135. So I'm going to plot it on that spiderweb graph. So that means that the r is 4 and the theta is 135 degrees. So what I do is I'm going to go out 4 units from that pole. Here's that pole again. And this positive axis here is called our polar axis. Move this over here. There we go. This is our polar axis. So what this tells us to do is it tells us to revolve 135 degrees. So that would be right around here, clockwise, and then go out 4 units. And there, right there, is my point. So in the polar coordinates here, at 135 degrees is going to be my point, P. So I would like you to try to find Q and R. Now, remember, I think we did talk about this last time and it was sort of intuitive, but if you have a negative radius, a negative R, then what we do is we take that point and we flip it about the pole. We flip it about the pole. So that's what happens if we have a negative value. And of course, if we did have an angle that was negative, we'd be going in the opposite direction. So let's see who we have here. Okay. So Ali, I would like you to try to plot the point Q. So you can either annotate and put it on the screen, or you can put it, yeah, I guess you would have to do that. So you would want to put that, try to annotate and put that point Q on the graph there. Benjamin, I would like you to try to go ahead and plot R. So again, you'll have to use the annotate tool. Caleb, I'd like you to try to find another point that's equivalent to 4 135 degrees. And Jonathan, I would like you to try to find another point that's equivalent to 4 135 degrees. Okay, so Michaela, I would like you to try to convert the point P into rectangular coordinates. Tomas, are you there?
Yes.
Okay, I would like you to try to convert the coordinate Q into rectangular coordinates. And Katie, welcome. I'm gonna put you on task, see what we can do here. So Katie, I would like you to try to convert R to rectangular coordinates. So a lot of you can just sort of enter things into chat. The rest of you will actually have to take control of my screen. So you'll have to go to annotate and plot those points there. So we're sort of recapping slash getting used to what we're doing here. So also remember, if you're trying to convert those two rectangular coordinates, we sort of know that this is the way we do it. Okay. Oh, yeah. You're asking for approval. Sorry. There you go. Awesome. Okay. Thank you, Ali. So that is point Q, right? Correct? All right. I'll help you out there. I'll give you an assist.
Okay, thank you.
Yeah. Oops. All right. So Jonathan gave a point. All right. It's going to be equivalent. Thank you, Jonathan. So in fact, 2 points. So I guess Caleb will have to find one that's not these two. All right. Or actually, there's just one there, which is perfect. All right, so Caleb will find another one. Okay. Caleb has 405 degrees. Okay, thank you, Caleb. All right. So Michaela and Tomas and I think Katie, if you want to, you can actually plot them on the Cartesian coordinate system, or you can just give me the coordinates of the Cartesian points, and I'll go ahead and do it for you. Okay, that's great. Thanks, Michaela. So that one is going to be our point P. Thank you. Awesome. Okay, and Katie says R is 1 square root of 3. Okay. 1 square root of 3, that would be around here, right? Michaela, do you have the coordinates of that point that you plotted there? Let's see. Okay, negative 2.8, 2.8. Okay, thank you. Alrighty. And let's see. Okay. And Tomas, oh, it looks like I assigned you both the same one, maybe. Let's see. Oh, wait. Oh, yeah, they're pretty much the same. All right. Okay. All right, so I guess we're just waiting for R to plot, or let's see. Oh yeah, that was Benjamin. Could you plot R for us, Benjamin? So R is going to be, oh, there it is. Awesome. All right, and I can, okay, go ahead. Awesome, very good. Okay, all right. I think that's everything. Okay, yeah, let's see. Let's go ahead and convert R over together into Cartesian coordinates, because I think I assigned two of you the same problem. Sorry about that. That was my bad. So thank you for taking a look at these. Hopefully this will get us back into the swing of things. So one thing you'll have to do on your final is you'll have to know how to convert these polar coordinates to rectangular and rectangular back to polar. But remember, they're a lot like vectors or complex numbers. They just depend on really like the moduli and the angle there. So the first one we wanted to graph here, I did P, so we're graphing Q. And Q is down here. Ollie has this graphed at negative 3, 45. So he swung around 45 degrees here, and then he reflected over this pole. Let's see here. Perfect. So he ended up with Q right here. Notice that this is going to be 3 out. It's going to be a radius of 3, and it's going to be in the opposite direction. Nice job, Ollie. So that's where you would plot Q on the polar axis. Are there questions there? All right, that's a great job. And now I sort of see that maybe this one is an R. I can change that sort of. Okay. So the next one was plotting R, and Benjamin did that. So if we look at R, it is a distance of 2 from the pole and 60 degrees rotation from the polar axis. So he is going to revolve around here 60 degrees, great, clockwise, and then he goes out 2 on that axis. So remember the sort of spider webs, the concentric circles, that's going to give you the R value, the distance from the pole, and the angle. So the like threads in the spider webs, the rays coming out, those are going to give you the theta distance that you revolve around there. Awesome, nice job. So P and R and Q look good. Okay, so now let's see how we have them converted over to their rectangular coordinates. Okay, so we can use these values of X and Y. So it looks like Tomas and Michaela gave us approximations, but we don't want approximations. We want exact answers. So what would the exact answers for those be? You two?
3.
For P. So if they plug in, they would have, okay, so the coordinates would be 4 cosine 135 degrees and 4 sine 135 degrees. So Michaela, what is cosine of 135 degrees?
Negative √2/2.
Yes, it is. Thank you. All right. So we can just plug that in. We can get an exact answer. And Tomas, what is sine of 135 degrees?
Drawing the blank here. 1 second.
Okay. No worries.
Is it the same? √2/2.
Exactly.
Negative √2/2.
So sine in the second quadrant, if we think about all students take calculus, so we're back here in the Cartesian, it'll be what?
√2/2.
Yeah, there you go. Great. So √2/2. All right. And these definitely are approximations for what we have here, but we really do. We didn't have you take that mastery test for nothing. We really do want you to put these in, and the software will be testing you on it as well. So if we do 4 times negative √2/2, that's going to give us negative 2√2, right, for exact value. And some of these you can't get exact, but these special ones you can. And then the y will be 4 or over 2, so 2 root 2. And those were good approximations for those two. Okay, so that's where p is going to be. All right. Great job. So also when you look at p, maybe let's see, that radius should be 4. So it's sort of, we're thinking of maybe out here. How to express that? Oh, that's probably about right, actually. Yep. I like that. Good job. So let's look at r. So Katie did r. She has 1 and root 3. So she just used 2 cosine of 60, or pi over 3. And that's x. And 2 sine of 60, that's y. And so cosine of 60 is 1/2. That gives you the 1. Great. And sine of 60 is root 3 over 2. So 2 times root 3 over 2 is root 3. Yes. Good job, Katie. Way to go. All right. So let's do q together. Q. So x will be -3 cosine 45 degrees. So we're trying to convert it over to rectangular coordinates, and y will be -3 sine 45 degrees. So who can give me the x coordinate?
Three root 2 over 2.
So -3 root 2 over 2. Awesome. And isn't sine the same thing?
No, it should be 3, not -3.
Oh, okay.
Oh, it's 45. Yeah.
Yeah. So
Yep.
so this makes it negative, right?
Yeah.
Okay. All right. And then it looks like your the one that you plotted in the polar coordinates, it looks like your x and y are going to be the same, right? And they are. So good. Cosine and sine are both negative root 3. Sorry, 3 root 2 over 2. Okay, so whoa, where is that? So -1.5 times the -1.5, almost. What is that? Almost -2.25. So I'm guessing it's going to be down around here. Nice job. Okay. And finally, these coordinates aren't unique. So if we're trying to find 2 other points equivalent to P here, then we have one of them that would be 495. So let's see what happened there when we plot this on our polar coordinates. So 495, we know we have to go around 360. And then when we go around 360, we have 135 left. So we're all the way back here. So this really just takes us around 1 and a little bit more times. And then we have our modulus, or our radius, distance from the pole, as 4. So this point is exactly the same as the one up above it. Now 4,405, that would actually be, let me think here, 405. So there's 360, 45 degrees. So that would actually be here. So this one's not quite going to be there. So who can give me another point that's going to be equivalent to that one? You might want to use like a negative angle or a negative radius, or yes, you could. Benjamin, can you give me one? Sorry.
Negative 45 degrees, -4.
Okay, so we do -4, -45 degrees. Okay, let's check that out. So I'm going to go -45 degrees. That's down here. Great. And then I'm going to go -4. So it's going to flip it across this distance of 4, and it's going to be right there. Perfect. So another one, nice job, Benjamin. Thank you for your help. So -4, -4, 45 degrees. All right, so you use both negative radius and negative angle, which is totally fine. All right. Nice work. So even though like the drawing is all messed up now, I claim that we have done some good work here. So are there any questions on those? All right. Okay. Let me clear this stuff out then. And whoops. Okay. Oh, why is it doing that? Let's see. Oh, I think that that's a Word deal. Word file. I don't know. That is weird. Oh, now everything I'm touching is turning to gold. Wow, like King Midas. So let's do file. Let's close it. And don't save. And then we'll try to open it up back up again if I can. Boop. Boop. All right. Sorry about that. So, all right. So, hey, this is going to be a good time actually to probably talk about what's coming up. So let me get that prepared for you. Stop share for just a minute. Thanks for being patient with me. You can tell it's been like over a week since I've done Zoom. All right, I think I'm ready to share now. All right, so share screen. I think that's the one I want to share. Let's see. Do you see my canvas? Yeah, all right, great. So here's my announcement. There's a lot of important information here, so I wanted to wait till you were all here. If you have friends that aren't here, please tell them about it. So based on your responses, I think I heard somebody leave. Based on your responses, I'll have, okay, he's coming back. Hold on, just a minute. All right, welcome back. So based on your responses from last time, I'm gonna have 2 final exam reviews, which is our last meeting, which is Thursday. So your class, the majority said Zoom. So I'm going to do a Zoom recording, and you're gonna just be asking questions. Good study tools are the final exam review, which is posted in Canvas. So if you go to Canvas modules, there's a final exam review. I've moved it up and published it. Those are really good things to look at that will take you back through the whole semester. So also old tests that I've handed back to you are other good reviews. So I will be here just to take all of your questions next time for the final exam. And I don't anticipate any new content. If you want to show up in person, I will have another final exam review on campus from 12:30 to 1:45 next time in Science 120. So you have an option of doing both, or one or either, or none. I'm not going to take attendance next time. I'll just be here to answer your questions, but it'll be a good time for me to answer your questions there. I'm going to record this session at 9:30, but when everybody's done asking questions, I'll probably just let us go. And this is the important thing down here. I do have 2 assignments in WebAssign and a Desmos project for you. They're all due on Thursday in 2 days at 11:59, and those will be our last assignments. Final exam information. So this is really important. You guys are my 9:30 class, so you're going to meet Thursday, December 9th. So we won't have another meeting until the final exam, Thursday, December 9th, next week. And that's going to be from 9:30 to 11:20 a.m. So you get an hour and 50 minutes in Science 218. So that's a different room. It's right up the stairs, but it's a different room, okay? So I just wanted to make sure that you knew that. That's where we're gonna have our final. And that will be it. Also, as you know, I've already dropped one of your lowest Desmos projects. So if you like the score that you have in Desmos, well, remember that the project's dropped there. You don't necessarily have to do this last one. This last one is pretty fun though. It goes pretty quickly. All right, so are there any questions that you have going into our last days of classes? Make sure that everybody's on the same page.
So to be clear, after
Yes.
this Thursday, the 2nd, we will not be meeting again until the final on December 9th, correct?
Exactly.
Okay.
You got it. All right. So this Thursday will be a great opportunity to review anything that you want to. All right. Okay. So now I'm going to try to open up that document again, and hopefully I won't be marking on it. Let me see if I can do that. Okay, so in modules, you can sort of see, hopefully, there's the final exam review. And we are looking at 8.5 and 6. Okay, so I'm going to pop that out, maybe. Come on, there we go. And download it. Meep. Okay. Open. Enable editing. All right. So do you see my notes now or no? Yes. All right, excellent. Thank you so much. I appreciate it. Okay, so now we're going to be doing a little more converting. So we're going to convert to rectangular coordinates and to polar coordinates. So let's go ahead and I will give you a little bit of time to try this out. I think it's important that you get your hands dirty with these. So I'd like you to try to do both of those. I'd like you to try to do both of those, and then we'll talk about it in just a minute. So try to convert the first set of polar coordinates to rectangular, and the second set of rectangular to polar coordinates. Now, the first one, you should be able to get exact answers. The second one, you're probably going to have to use your calculator or Desmos to get approximations there. So give it a try, please. While you're doing that, I'm going to go ahead and draw these out. I'm going to show you where they are. Second one. All right, I'm sort of looking at you, trying to gauge who I think is ready. It's been about 3, maybe a little more minutes. Does anybody need 1 more minute? Anybody? No, you're all ready? Okay, all right. Okay, so let's look at that first one. So we wanted to change that into rectangular coordinates. And so the first one, I'd like you to type it in chat, and we're going to send it here in just a minute. So this should be coordinates. If there's like a square root or something in there, you can do SQRT, or you can copy the square root symbol, whatever you want to do there. All right, so we're going to send it here in just a second. So in 3, 2, 1, let's send that first one. Send that first one there. All right, 3, 4, 5, 6, and 1 more, 7. Yes. All right. So 6, -2 root 2, 6, 2 square root of 3, 6, 2 square root of 3, 6, -2 square root of 3, -4 square root of 3 over 2, -6, 6, 2 square root of 3, 6, -6, negative square root of 3, 2 square root of 3. All right. So there is a lot of controversy here. All right. Okay. All right. So we know that one of those coordinates has to be negative based on how I drew it, right? So one of those coordinates has to be negative and the other one has to be positive. So if you'd like to revise, go ahead and put that in chat. It's one thing we know. Okay. Okay. So now 6, -2 square root of 3 is sort of rising at the top there. Okay. 6, -2 square root of 3, and then 4 square root of 3 over 2, which would be 2 square root of 3, -6. Okay. Okay, so yes, the y coordinate has to be negative, and it turns out here, okay, it looks like we just have, this one was a sort of a tough one, I think, because the small angle was pi over 6, right? So that's the 30-degree angle. So what that means is this side is going, it's a 30, 60, 90, but this side is going to be the smallest across from the angle. So that one would have to be half of the hypotenuse, or -2 root 3, right? So it's going down. And then the bigger side would have to be root 3 times that. So root 3 times that would be -6, but we're going in the positive direction, so that would be 6. So this one is 6, -2 square roots of 3. So you can definitely do that by using that 30, 60, 90 triangle, or these should be equal to 4 root 3 cosine of 30 degrees, or -30 degrees is the same as 30 degrees, and 4 root 3 sine of that negative square root of 3, or sorry, negative square root of 3. I don't know where I'm getting that. I'm messing that up. Negative pi over 6, 30 degrees. Okay, so yeah, so this would be equivalent to the rectangular coordinates of 6, -2 root 3. Questions there? So it looks like eventually most of us got it. It's good that we sort of go between radians and degrees, because that one with the pi over 6, that's not actually 60 degrees, that's 30 degrees, and the pi over 3 is going to be 30 degrees. Okay. Pi over 3 is going to be 60 degrees. Okay. So what about number 2? So that one, we're given rectangular coordinates, but that's not a special triangle. So we probably had to use our calculator to at least find the angle, right? We could probably find the radius exact, but the angle would be sort of a problem there. Now let's remember that it is in quadrant 3. So are you ready to type that one in? All right, go ahead and give it a shot. So type it in. And in 3, 2, 1, go ahead and send it, please. 3, 4. That's a little more than half the class. 5, there we go. 6, there we go, there we go. Okay, thank you, I appreciate it. So square root of 13 and 33 degrees, square root of 13 and 213.7 degrees, negative square root of 13 and 33 degrees.
That was a typo. The negative isn't supposed to be there.
Okay.
My B.
Oh yeah, okay, yes. So the negative's not supposed to be there in yours, but it may be there in Caleb's. And then square root of 13, 33 degrees, square root of 13, negative square root of 13, 34 degrees, plus or minus square root of 13 and 33.7 degrees, and square root of 13, 213.69 degrees. All right, so you know what? I can't argue with you giving me 2 values there, because you know these could be, there could be 2, like there could be infinitely many of them, right? So this is the one that I got. However, we'll see if some of the other ones are correct. So for the radius, and it looks like everybody was getting the radius correct, it's just going to be the square root of 13. So we just use our good friend, the Pythagorean theorem. For theta, I used tangent of theta was equal to -2 over -3. So that's really going to give me a positive tangent. So when I take inverse tangent, I got approximately, I think what you all got, 30, I didn't write it down. Let me see. No, 33.7 degrees. So I rounded it to 33.7 degrees. All right. However, when I look at this point here, it's in quadrant 3, right? So this makes a good reference angle. But to get over there in quadrant 3, we would have to add 180 to it, right? So that gave me, 213, I think, I can read my writing, 0.7 degrees. So yeah, perhaps one possibility could be square root of 13, 213.7 degrees. So we just need to figure out which quadrant we're in there. However, I'm sort of intrigued by some of your other answers. So if you had like a negative square root of 13 and you had the 33.7 degree angle, I would buy that as well. So here is our 33.7 degree angle. And if you had negative square root of 13 with that, it would reflect it about this axis and bring it right where it should be. So I would buy this coordinate as well. So this one would be there. Now let's see, negative 33.7 degrees. I'm not buying that one because it's going to put us over here, or if you flip it, it's going to put us here. Okay, so probably the most popular answers would be these 2. Sound good? Are there any questions there? All right, excellent. So let's keep going. All right. So we can actually graph these things in polar coordinates, and we're going to be looking at that very briefly in the next section. but I'm going to have you use Desmos in your project to sort of look at some of those prettier graphs. When we have equations in polar coordinates, we can actually think about those in rectangular. So we have to remember our conversions though. So when we were looking at, when we were looking at R, we have these conversions. We know that x squared plus y squared is equal to r squared. We know that x is equal to r cosine theta. We know that y is equal to r sine theta. And we also know that, probably not as important, but tangent of theta is equal to y over x. So we have all these conversions that we can use to convert from rectangular to polar and vice versa. So when I'm doing this, what I want to do is if I have something in polar like these two are, I want to make all the r's and thetas go away, and I want to come up with something in terms of x and y. Now, some of these, like we talked about, won't be functions. So we won't be able to plot them with our calculator, but some of them will know the graphs from those. So this first one, I sort of just look, I see this r squared. I'm like, hey, yeah, r squared. I know that that's equal to x squared plus y squared. So I'm just going to put that in there. And I can't really solve this for y. So this one wouldn't be a function in rectangular coordinates, but would you know what that graph looks like for just knowing about rectangular coordinates? So an x squared plus y squared is equal to 9. Let's try to plot it with rectangular coordinates. Any ideas? Go ahead, Ollie.
Maybe x. No.
Okay, I saw Benjamin's hand.
This has multiple answers.
Okay, so
Not all of them would be in the same spot. Because multiple things can add up to 9.
Yeah, exactly.
Yeah.
I like that. I like that logic. So we're thinking about I like that logic. So when you're thinking about it, it sort of makes more sense in polar. When you're thinking about the radius squared is equal to 9, then if you took a square root, the radius would be equal to plus or minus 3, right? So if you thought of theta as being sort of arbitrary, and everything that's 3 or minus 3 from the pole, where would that put you? What kind of figure would that give you?
Could you repeat the question?
So if I was thinking of this, it's sort of a good polar question. So if I have the radius squared is equal to 9, if I solve that for r, I would have the radius r is equal to plus or minus 3. But theta is arbitrary, so theta can be anything. So what sort of graph would we map out if we just had that radius equal to 3 or minus 3? Go ahead, Benjamin.
That'd be like a circle. That'd be a circle of 3,
Exactly.
of radius 3, yeah.
Exactly. Great job. Nice job, Benjamin. So this, if you don't recognize it in Cartesian coordinates, well, it's been a long time since you've taken college algebra. Okay. We did sort of discuss this way back in chapter 1, but moreover, when you're thinking of this in polar coordinates, this just basically says, okay, the radius squared is equal to 9, and theta can be arbitrary. So it would say the radius is equal to either plus 3 or minus 3. And when you think of all those points that are going to evolve when you go plus or minus 3 from that pole, you get that circle of radius 3. So that's exactly what this graph looks like, a circle of radius 3. All right. Now let's look at this next one. So here, it looks like we want to use these x and y are equal to r cosine and r sine. But maybe I would have to distribute this in first. So if I distribute the r and I have r cosine theta plus r sine theta is equal to 3. But r cosine theta, I can replace that by my x coordinate. And r sine theta, I can replace that by my y coordinate. And I have x plus y is equal to 3. I can actually solve that for y. That's going to be a function. Y is equal to negative x plus 3. So what kind of graph would that give me? You can feel free to shout it out.
A linear graph.
It's gonna be a line, yeah. What's
Yeah.
the slope?
It'd be -1 do. No, wait, no. No, it'd just be it'd be -1.
-1 is the slope. Great. And what's the y-intercept? Because that's how we usually define lines.
It'd be 3, I believe.
Yep, 0, 3. Perfect. Nice job. Thank you. So it's going to be, this one's just going to be a line. It's a linear function. And it's going to have slope -1. So it's going to be decreasing. And it's going to go through that y-intercept. It's 0, 3. Perfect. So when you look at these graphs, this first one is going to be a function in polar coordinates, but not a function with rectangular coordinates. So when you're thinking of something circular, I think that you would all agree that polar coordinates would probably be the way to go. When you're thinking of something as a straight line, this is probably more complicated than something that we can turn into a function here. Now, I guess we could actually turn this into a function in terms of polar coordinates, interestingly enough. We could solve for r, right? We could say r is equal to 3 over cosine theta plus sine theta. So that would be our equations of a polar line. Weird. But this makes a lot more sense from what we learned in algebra. So it looks like maybe the moral of the story is circular graphs work better with polar coordinates and linear graph work better with Cartesian coordinates. Okay, but you can switch those around. And part of your Desmos project will be sort of experimenting with some of those more polar graphs. All right, questions there? Okay, let's go on to our last section. That's for now. Okay, so these are actually, this is just sort of a quick rundown of graphing with polar coordinates, and so polar coordinates and their graphs. So when we're thinking of rectangular Cartesian coordinates, we're looking at points described as x comma y, and functions y are equal to f of x. With polar coordinates, we now know that our polar coordinates are described as r comma theta, and functions look like r is equal to f of theta. So when we look at like x is equal to something without a y, or y is equal to something without an x, when x is equal to something without a y, that's just going to be a vertical line. X is equal to 3, x is equal to -1. When y is equal to something without an x, we have a horizontal line. So it might make sense that when you just have those x's and y's equal to a number without the other one, you're going to get the Cartesian grid. That's the same thing that happens with the polar grid. So when you have something where you don't have an r, so theta is equal to an angle like alpha, what this gives you is a line that goes through the origin. So it's going to give you a type of graph that looks like this. So let's say that we have theta is equal to 45 degrees, or theta is equal to pi over 4 radians, then really r is free to be what it wants to be. But theta is stuck at 45 degrees. So that sweeps out this line. So essentially, when we have theta without an r, we are mapping out all these linear graphs that go through the origin. And that is like the turn of our angle in polar coordinates. So that's a grid line in polar coordinates. When we have r is equal to something without a theta, that is going to give us a circle. Because in this case, so like, let's say that we have r is equal to 2. That will give us the other grid line. So we know that r is equal to 2, and theta is free to sweep along however it wants to be. So these, it might make sense to you that when we have polar coordinates with just an r, just a theta, that we actually get the axes, these nice points on our axes, just like we did with rectangular coordinates. All right. So again, the ones that describe the circular graphs are a little more interesting to us, and not so much with the lines, because we can plot those in Cartesian coordinate system. So one thing we want to do is, eventually we want to be able to plot some of these graphs. And again, that's what the Desmos project is going to do for us. But one way to look at plotting these graphs is actually, just like you would do in Cartesian coordinates, plug in points. So I want to look at this one. I want to look at what the graph of r equals cosine theta would be by plugging in points and evaluating them. So I'm going to need a little help. So everybody pick one. I'm going to have Ollie do the first one. I'll do 0 for you. Ollie, think about plugging in 30 to that graph. Benjamin, think about plugging in 45 degrees. Caleb, plug in 60. Jonathan, plug in 90. Michaela, plug in 120. Katie, plug in 135 degrees. And Tomas, plug in 150 degrees. And I think I've assigned one to everybody. And you're going to plug it into that graph, and then you're going to just tell me what you got for that. And we'll plot those points after you get them. So I'm going to go ahead and plug in 0. So r is equal to 4 cosine 0. Cosine 0 is 1. So 4 times 1 is just, 4. So that's what's going to happen when I plug in 0 to that graph. So my first point here is 4, 0. Right there. All right. So when you plugged in 30 degrees for that graph, what did you get?
2 square root of 3.
Okay. Square root of 3. 2 square root of 3. Excellent. Yep. So cosine of 30 degrees is root 3 over 2. And 4 times 3 over 2 is 2 root 3. Benjamin said that when you plug in 45 degrees, you get square root of 2 over 2. So that's 2 square root of 2. Excellent. All right. Tomas is plugging in his. Okay, so you can go ahead and put those in. Or you can just tell me what happened when you plugged in 60 degrees. Who had that one?
I got 2.
Okay, great. Nice job. Good job, Caleb. So cosine of 60 is 1/2. 1/2 times 4 is 2. Who had 90? Nope.
I got 0.
Excellent. Very nice. Cosine of 90 is 0. Who had 120?
-2.
Okay, perfect. That's going to be -1/2. So notice the symmetry here. You sort of see the symmetry. That's just in quadrant 2. Who had 135?
Me, I'm not very confident in my answer, but I got -√2 over 2. So.
Yeah, so it's -√2 over 2 times 4. So that'll be -2 square root of 2. Yeah, that's perfect. So again, you can sort of see the symmetry here. This one would match up with this one, except for it's going to be negative because it's in quadrant. It's in quadrant 2. Oh, the one for 150 went away. What did you get for that for the 151? Okay. -2 square root of 3. Perfect. All right. And then 180, wouldn't that just be -4, right? Okay. So we can plot some of these points. Thank you so much. You did a great job. You all did a great job. So 2 root 3, 30. You know, 2 root 3, we can sort of cheat on our calculator. It's not really cheating. Just don't know what that is. So that's about 3.46. So if I go to 30 and go out about 3.5, I'm about right here. That's going to be the 30-degree point. If I sweep out 45, 2 squared of 2, you told me that was about 2.8. So that would be like right about here. Perfect. And 60 degrees is exactly 2. Okay, that would be about here. And 90 degrees is 0. So that would be right at the pole. And then if I go 120 degrees, I have to flip over to -2. Okay, great. And if I go to 135, I have to flip over, and that's about -2.8 right here. And if I do 150, I have to flip over, and that's going to be about, what did we say that was? Well, it's equivalent to that one. Oh, I have it right there, 3.5. So right about here, maybe close to that. And then at 180, I plug in and I go back to -4. So I'm guessing that if I kept going here, so 210, that I'm just going to get these same sort of values out. It's just going to keep revolving around the circle. So 210 would be equivalent to 30, but it's going to be negative. 235 is going to be equivalent to 45, but it's negative. So my claim is 240 is going to be the same as 60, but it's negative. Oh, and now I'm in 315. So I've jumped over to quadrant 4, and those are positive. So that's going to be a 2 root 2. And then 360 is going to be back at 4. So I claim that that's just going to revolve around the circle again. So this turns out, if I mapped all these points out, you get a circle. Okay. And if I kept going, that actually mapped out in 180 degrees. So this whole circle had a domain, or would map out and 180 degrees. And then we would just keep going around it if we kept plotting points. So what do we observe about this circle with cosine? Like, for instance, where is it centered and what's its radius?
I think 2, 0 is center.
Yep.
The radius is 2.
Yeah, exactly. Nice. So when we sort of look at cosines of angles there, you might be able to make a conjecture, and it's true that your if your cosine is positive, so if that's a positive radius, we're actually going to be going out to the right. So that circle is going to be centered out to the right, and it looks like maybe the center is going to be the square root of that number out in front of it. So the furthest it goes out is 4 from the pole. And so we'd have our center at 2, 0, and our radius would be that square root as well. Whoops, yeah. Nice. So you can actually do this on your calculator. Whoa, so what you want to do, if you want to try this at home, is go to mode. So in your mode, you're going to switch from function to polar coordinates. You see polar coordinates there, switch from function to polar, and I'm in degree mode. So we'll just want to make sure that our domain goes to degrees. So I'm going to go to polar mode. And when you go to polar mode, and quit out of there and then go to y equals, look what you have for y equals. It's like r and theta. So you're just going to want to put in that graph, and your x will be theta now. So I'm going to go ahead and put that in. Let's see here. So I'm going to put in 4 cosine x, but that should give me a theta. So it should look like this, 4 cosine theta. And then I'm just going to make sure that my theta values I plug in are in degrees. So perhaps I would go to window. And it looks like I'm in radians now when I go to window. That's bad. It's not necessarily bad, but if I'm going from 0 to 6.28, I'd probably want to turn everything into radians. So at this point, I can either turn these into degrees, or I can just change my mode to radians. And I think I'm just going to change my mode to radians. That's probably the easiest fix. So I go back into mode, hit radian. And now the moment of truth, I'm graphing it. Ah, okay, so this is what I got when I graphed it. So it looks like it's going to go around, but it doesn't look like I'm going to get that whole thing in. So perhaps I can go to window. And they still do X min and max. So to get this in, it looks like in my my graph there, I went from -5 to 5, and maybe I'll just do in steps of 1, and then y went from -5 to 5. So I just sort of modified that a little bit to sort of hopefully give me the same thing that I have there on my screen. Try that graph. Oh, well, it looks sort of ugly. It looks more like an oval, right? So one last thing I might want to do is go to window. And I'm going to go to zoom, and I'm going to push zoom square. I'm going to do a zoom square and see if that helps me out. See if that helps me square things up. Okay, it did. Oops. So that's more like what I want there. Okay. So you can actually plot these using polar coordinates with your calculator. However, you just have to be careful, because depending on whether you're in radian or degree mode, you will have to switch your window accordingly. Okay. All right. Nice job. So hey, these problems not only help us plot pretty graphs and help us learn polar coordinates, but they also give us a built-in review for the special values. How's that for? So I told you we'd be looking at them the whole class, so I'm not lying. Questions there? Yeah, go ahead.
So here we have r equals 4 cosine theta.
Mm-hmm.
So is 4 diameter of this circle?
It sure seems like it, doesn't it? So we could experiment around, couldn't we? So let's see what happens here. I'm gonna just type this in my calculator, and now that I've plotted 1, yeah, that's a great thing to do. Like, I'm gonna change it to 5 and graph it, see what happens. Okay. Oh. Let's see here. Let me see. I'm not there yet. It did change it. Sorry. Let's see. Whoop. I'm too close. No, I'm actually.
Yeah, actually the light.
The light is weird, right?
Yeah.
There we go.
Yeah.
So that one is 5 units. Yeah. So the diameter is 5. Yeah. I don't know. What if I changed it? Yeah, that's good. Well, I'm going to change it to -2 and see what happens. Okay.
Yeah.
So
it's the other side.
that's your conjecture. And what would the diameter would be 2? Let's see. So I'm going to type in -2 cosine theta and graph it. Let's see. You were right. Yep. So that's going to flip it to the other side, and your diameter would be 2. So yeah, so you can play around with these all that you want. And now what if you had like 2 sine theta? What do you
And
think that would?
why
Yeah,
axis?
exactly. So your intuition is correct there. Very nice. Okay. And that Desmos project will let you sort of experiment with those. All right. So I had another one. Okay, so this one, I had another one that we're looking at here. The thing with the double angles in there is you have to be really careful because now if you just plug in your special values, you're not going to have enough points if you plot these by hand. But this gives us a good chance to sort of experiment with things on the calculator. So we thought that this might move it up and down. I'm going to go ahead and just put this in my calculator since we're sort of short on time here. All right, but yeah, your intuition was totally right there. Okay. All right. So we have these class of graphs that sometimes come out depending on the angle theta. So we can make a lot of really pretty graphs here. Notice that this one, that's sort of weird because doesn't that one look like the one that we just plotted on my calculator? 4 sine 2 theta. So it looks to me like when you double that angle, we should get more. We should get these rows graphs, but that's not what we got, was it? So did I type in this correctly? Oh, you know what? I forgot to type in 2 theta. My bad. Was there a 2 theta in the other one? Yeah, there was a 2 theta. So that was the deal. My bad. I did not type in the correct thing. So when I type in 4 sine 2 theta, if it was just theta, you would be right. In fact, you just saw it. Okay. So you saw the one that I typed in, but if I type in 4 sine 2 theta and graph it, then it comes out with this nice 4-petaled rose. So this is sort of how we classify graphs, and this will be it for the class. So when you have cosine or sine of 2 theta, you get double the amount of petals. And you can sort of see that the sine is rotated and the cosine's not. When you put in an odd angle, you actually get exactly that many petals. So that's sort of interesting with these polar graphs. If I put in an odd number, I get exactly that many. If I put in an even number, I get double. We have graphs called limnoscates. They look like infinity or infinities on the side. And those are squared or equal to a cosine 2 theta or a sine 2 thetas. These are my favorite, the cardioids. So if you think about like going into cardiac arrest, or it's a heart, right? So cardioids will be something like a plus a cosine theta or a plus a sine theta. And it sort of depends on whether we have it centered on the X or the Y axis. You'll be experimenting with those. And then sometimes these little cardioids can have a loop in them. So you'll be experimenting with those with the Desmos project. Okay. So that's all I have for today.